Let's have a look at the basic principles behind GPS and how it operates. So GPS is used for navigation and location on Earth. That's the reason it's called a global positioning system. And essentially it's able to give us latitude and longitude. Okay, so latitude is how much north or south a location might be. So that's usually, if you look at it from the South Pole, and you're looking at it in terms of a globe over here, that would be at 90 degrees south, or it might also be referred to as minus 90 degrees. Equator, which would be in the center, that would be at 0 degrees, and then north would be at 90 degrees north, or it could also be referred to as just 90 degrees, being a positive value. Okay, longitude is how many degrees west or east your position might be. Okay, so again, if you look at your specific globe that you might have, you will realize that there's these lines that are going across in this type of fashion. Okay, so we've got 0 degrees at the center, which should be over here at 0 degrees, and then usually these segments would go at maybe 15 degrees or so, either to the east, which would be this direction, or to the west. Again, as you're going towards the east, these might be positive values, so it would be like 15 degrees to the east or 30 degrees to the east. At the same time, you could have 15 degrees to the west or 30 degrees to the west. And a way to differentiate between the east and the west is that west would often have a negative connotation like that. So in this way we're able to identify our positions, and keep in mind that longitude goes from 0 degrees up to 180 degrees, which would be to the east, and then also, so that's 180 degrees, and then also to a minus 180 degrees, which will be to the west. So 0 degrees goes through the Greenwich Mean Line, which is located in London, and that is where you'll find your 0 degrees, and then it goes to either side of the Earth. Right, so this is an aeronautical chart of the Johannesburg area. Very complex chart that is used in aviation. That gives a lot of information about the different airports, areas that you're allowed to fly in, restricted areas that you're allowed to fly or not allowed to fly in, and quite a useful map also to navigate around your way, depending on where you're going. And a typical map like this would have at the bottom the degrees. So you'll see that over there we've got 27 degrees, and then we've got 28 degrees, 29 degrees. So that's indicating how many degrees we are moving towards east. So Johannesburg is roughly 28 degrees to the east. And then you also see that there are other lines over here. Like for example, you'll see over there is a 26 degrees south. Then as you move down, you'll see that eventually you get to over here, which says 27 degrees south, and that would indicate obviously how far below of the equator we are. So a lot of these features that are experienced in the GPS is essentially just a digital way of representation of this map that we often would be using. Okay, let's have a look at what GPS is able to offer us using a software package like Google Maps. So with Google Maps, I can actually go and I can click on a specific point, and it will tell me over here exactly what the GPS coordinates is. So at the moment, it's telling me it's negative 29.859142. That is, and then obviously that would be in terms of indicating that we are south, and south is referred to the negative sign, while north would be the positive sign, and then 30.969293. And that's a positive value, which indicates that it should be so many degrees to the east, while west would be a negative value. So that is how longitude and latitude values are shown over there. Fortunately, it's got the option that it will be able to tell you where your location is. So from this, it's able to identify where my location is, and once I've done that, I'm able to then be able to find direction. So for example, I could say, well, I want to go to a specific point, and it might be over there, and I will ask, okay, I need directions to that specific point, and it will be able to show me how to get there. I can give also a starting point. So let's say, for example, I'm wanting to be at let's put in a address over here, George Campbell building at the university. I click over there, and it's able to give me all the different directions and routes that I'm able to follow. It's also, what's also quite nice is that it can give you different routes. So for example, the one might be 3.7 kilometers, which is further, but the fastest route is giving me a warning that this has got restricted usage or private roads that need to be followed. And that's very typical over here, where there has to be some of these roads are going through campus, which is restricted to normal public. And so it allows us to sort of navigate our way around as well. We're able to also look in terms of walking. That would possibly give you different routes sometimes. It might take shortcuts through grass areas or so. And also, what really is also really nice in terms of this GPS applications is it's able to give you sort of a profile that you're going to have to travel. So you can sort of know, if there's going to be a lot of uphills or downhills of walking or traveling that might be needed. Okay, so let's have a look at how these satellites are able to identify where your location is. So the satellite receivers know the position of the satellites orbiting the Earth. Okay, and these satellites have got atomic clocks in it. And these atomic clocks are very accurate in terms of keeping time. Okay, so essentially, let's say you are on Earth, you're located over there. There might be a satellite that is over here, and a satellite that is over there. Now these satellites transmit out a signal to the receiver in that fashion. Okay, and what's happening is because the receiver, which is located over here, knows the position of the satellites, it knows the distance that is from the satellites to the receiver, and therefore it's able to then identify what the time period is for that signal to be received. And with the intersection of these signals, it's able to then identify the actual location. Okay, so keeping that in mind, let's have a look at on a two-dimensional type of view. So we've got, for example, satellite 1, which is over here, and that is transmitting a signal on the Earth, like so. And you might have another satellite that is transmitting a signal on the Earth, like so. So keep in mind, it's in a two-dimensional, it's a circular pattern that might be transmitting down onto the Earth, depending on where the satellite is. Now, if you've got two satellites, these intersections of these signals that is where it identifies where your location is. But if you look at these two satellites over here, you could either be located at this specific point over there, or at this specific point over there. So, to eliminate that error and to know exactly where you are, you actually need a third satellite for this 2D scenario. So, having a third satellite that will be broadcasting a signal over there will have three intersections, and therefore you would know, well, I can't be at this position over there, I've got to be at this position over there. Okay, so that's the reason why three satellites would be needed for a two-dimensional type of environment. Yet, because satellites have got availability to give us altitude as well, at least in terms of altitude above sea level, the same scenario is happening in a 3D type of environment. And due to this 3D environment, to be able to make it work, you need a fourth satellite. So for an accurate measurement, okay, you need to have at least 4 satellites as a minimum. Okay. The more satellites you've got, the better the accuracy can get, and therefore eliminate any errors that there might be, which are like errors such as reflection off the buildings or so, like we've discussed. Okay, now something also that's important with these satellites is if you look at these signals that are intercepting each other, if the satellites are very close to each other, so for example, we've got one satellite that is broadcasting a signal up to that point. I'm now zooming in onto those circles that we've just been looking at. And another one is transmitting in this fashion. It means at this intersection point, if you look at it, there's sort of quite a broad area that we don't know exactly where the satellite might be. You might start asking the question, is the intersection at this point over there? Is the intersection at this point over there? Maybe at this point over there. It's so close to each other. And that section over here is known as the region of uncertainty. Okay, so essentially what you want to do is these satellites must be as far apart from each other so that you've got more of a 90-degree intersection of those signals compared to having this type of scenario where we've got a large region of uncertainty and it's difficult to pinpoint the exact position that you are. Okay, so there are other ways that you can also be used to eliminate these errors in the GPS, and one of the ways is what's known of differential GPS. Okay, differential GPS, how it operates is that it knows a specific point on the Earth. It will actually have a GPS over there. So this is a known position, and it will take the reading of that GPS signals that are being received. And if it knows that, oh well, there is some error that is happening, so let's say it identifies it as an error of 2.1 meters compared to the actual known position, then you might be located at this specific point, with your little GPS. And what would happen is you would actually be getting the information of this known error, which will be transmitted from this known location to your GPS unit, and it would correct this GPS reading with this 2.1 meter error. So a lot of the airplanes might be using it. It also gets used a lot in the drones or the unmanned air vehicles, and to be able to just get this error eliminated and to be able to navigate more accurately. The Silver Shark is an autonomous boat that we developed recently. It's got on board a GPS, a gyroscope, accelerometer, and a compass. It's able to go to different waypoints, and there's no interaction required from the user. You can actually let go of the remote and it'll be able to go to those different waypoints. Once a waypoint is obtained, it goes to the next waypoint. So you're able to monitor location of the autonomous boat as well, and we've been using the geotab system as seen over there. Then the autonomous flight and packaging delivery system was made so that we can deliver packages like medical supplies in a deserted area. It's able to take off automatically and fly to different waypoints as well. It's able to detect the wind speed and the direction, and then from this be able to deploy a package on a red circle that's 0.4 meters in diameter at a height of 75 meters above the ground. I've been going on a ride here in the bush trails and been able to record the distance I've been going with this off-road mountain bicycle of mine. So how it essentially works is that your bicycles have got this magnet mounted on the front wheel, and as it goes past the sensor, it is able to then detect that a full cycle or rotation of the wheel has occurred. Now this sensor in here is either a reed switch or what's also known as a Hall sensor, and it's able to pick up these magnetic fields as the magnet passes through it. As soon as it detects the signal, it transmits it wirelessly to a computer on the top of the bicycle, and I can observe speeds, distances, and certain related activities that I've been involved with. Okay, so there's a few things that could influence the readings. The one is, and obviously these readings cause this error as well. So the one issue that could cause errors in our readings is this magnet could be positioned maybe incorrectly, and so the sensor is not able to pick it up every time. Other aspects that can cause error in the readings is that the diameter of the tire could be different to actually what it's calibrated on the computer system. You could also find that the wheel diameter can change due to things like the tire thread that's worn away. It could also be in terms of the tire that bulges because it might be not inflated as much as it's supposed to be. And so there's also a common thing that you might see happening with a car. A lot of people would maybe go and put on larger wheels or rims and think it looks really smart, but that obviously affects the diameter of the wheel and therefore influences the actual speed that you're going, at least what you're recording. Other aspects that could also have influenced the readings and give an error is that as I was going downhill, I could have braked to prevent going too fast, and that could have caused the wheel to skid. So it's going downhill, but it's not detecting any motion because the magnet's not moving. At the same time, I could be going up a hill, and as I'm going up the hill, I might be trying to lift up the front wheel and get it to go more easier up and to go over obstacles. So obviously when this happens, the wheel is not turning, and that also influences the movement and therefore the recordings that we are able to observe. The bicycle computer is able to give me details such as what speed I'm going at in kilometers per hour. It gives me the distance I've done in and indicating over here is 1.21 kilometers. It tells me the runtime of 8 minutes and 45 seconds. The average speed I've been going is 8.2 kilometers per hour, and then the maximum speed that I've reached shown by this computer is 15.7 kilometers per hour. So I'm able to use an application on my phone that's able to use your GPS and do the recordings. So as you can see over here, the route that I actually took is shown over there, and you're able to see the altitude as it increased. You can see that I went up a hill and then came down a hill again. So those are all visible over there. And then I'm also able to see what distance I traveled. It recorded 1.22 kilometers. Now that is a bit different to what the bicycle computer recorded. And again, it is because there's the satellite view, or at least what the satellite or the receiver is able to see the satellites is always a problem, and that needs to be taken into account. When I start off the recording, it tells me that the GPS has got an accuracy of 23 meters. So there could be some error in terms of that as well. Then if you would, for example, also have a situation where there will be trees, there will be leaves, there will be water in the leaves, and these obviously also absorb signals, especially those that the satellites are transmitting at, and this will also give us errors. You also find that a lot of times signals can bounce off from buildings or concrete surfaces or even metallic surfaces, and this could give you a longer distance that is the signal has traveled from the satellite to the receiver. So those are things that could cause these errors to actually happen. So I've got a distance of 1.22 kilometers. It tells me my moving time is 8 minutes and 50 seconds, while the computer indicated 8 minutes and 44 seconds. Average speed was 8.3 kilometers. So this is, or 8.3 kilometers per hour. Units are always important. And so I got an average on a bicycle computer of 7.9 kilometers per hour. Then the elevation gain is also given over there, which tells me how many meters I actually climbed. And then rough calculation is done to determine what your average power and calories is that you've burned, and this always takes into account the weight of the person, the weight of the bicycle, and then the distance and the speed that you were traveling. So what's quite nice is it allows me to use this GPS feature. I can then zoom in and see where I've been able to ride. I'm able to have a look at the satellite view as well, so you can see I was going around a field, going up into a forest area, and then came back. And so what's quite nice with these satellite views, even though they're not always updated views, I can always zoom in and see exactly where, or roughly where I went. You would also notice that there's a little bit of error that might be seen over here in terms of like, for example, it seems that I've been going through bushes over there, so there is a slight error in the actual path that I went, and also the satellite image is not necessarily overlaid perfectly exactly where you would have been going. I can also, with the GPS, it also allows me to do analysis. So I can look at the profile that I went up with in terms of the elevation. So like I said, the elevation gain was 34 meters. So that's roughly 110 to about 75 meters, that distance over there. And then the maximum elevation that I went, or maximum altitude that I was 110 meters, as indicated over there. And then also these apps are quite useful, as it allows me to see how I'm the speed that I've went, depending on what elevation I went. So you would see some areas there would be that I would be going slower as I was climbing up with the hill, and in other places you see where it's actually I might be going faster as I'm going down the hills. So it just depends on the terrain that was happening. So these type of applications and GPS recordings are really useful when it comes to training, for example, with cycling. Right, as you can see, the different readings were obtained from the computer and GPS. Okay, so if you look at the distance that was traveled, according to the computer, 1.21 kilometers was traveled, while the GPS indicated a value of 1.22. Now, because the computer had the advantage that it was able to take recordings maybe underneath the branches of the trees where the GPS wasn't able to get necessarily a good signal, it might have been more reliable compared to the GPS signal. At the other times, it might have been that the computer wasn't working well because you were skidding as you were going down a hill, while the GPS was still doing a recording. So it's often important to use different sensors to be able to get or obtain your readings, which might use different methods to obtain those readings. So in this case, it's a good thing to then obtain the average, and you'll probably get a more accurate reading. So the average of the distance would be 1.215 kilometers. If we look at the time, it was 8 minutes and 45 seconds that was traveled. GPS found it to be 8 minutes and 50 seconds. So again, taking the average of that leaves you with 8 minutes and 47.5 seconds. Now then, if you look at the speed, the computer was able to find that the average speed was 8.2 kilometers per hour. The GPS was able to find average speed to be 8.3 kilometers per hour. So obviously the average would be 8.25 kilometers per hour. And then if you look at the maximum speed with the computer, it indicated to be 15.7 kilometers per hour. The GPS found a maximum speed of 17.3 kilometers per hour, so therefore the average speed would be equal to 16.5 kilometers per hour. So as you can see, different sensors have got its advantages. Some of them are able to get readings better in certain conditions, while others might not, and vice versa. So it's a good thing to have these combinations of sensors, and then there are ways that you can incorporate those sensor values together using data fusion techniques, or you could use find the average of it to be able to know what the average speed is, which could give you a better value compared to the actual values that were obtained from each individual sensor.